All right, so last time we talked about topic model for single topic documents. We finally learned how to use moment matching to learn model parameters with consistency guarantees. We also learned that in order to learn the model parameters for latent variable models, we usually require moments higher than second order moments. We would need first, second, and third for a wide class of latent variable models. Actually, 3 is enough for learning the following. For example, mixture of Gaussian, latent Dirichlet allocation, um, single topic model, multi-view model, actually for conditional independent, so for ICA, conditional independent component analysis, you would need like a fourth order moment. But so the message here is for a wide class of models, need only lower order moments, but usually greater than 2 and smaller than 4, right? So typical is like 3 is enough. But so no, some of you might ask, do I need more than 3? The answer is no, you don't, but you can use more than 3 for a lot of scenarios, right? It's just that, so if you go to higher order, your sample complexity will be higher due to concentration bounds, as you can see. So you need more samples to make a accurate estimation. So usually people would want it to go as low as possible, but high enough to uniquely identify the models. So overall, that's a recap of what we did last time. But so last lecture we said everything reduces to doing a tensor decomposition, and we learned some notations about tensors, right? We learned about slice, we learned about fibers, we learned about how to decompose a tensor in its CP form. So we learned how tensors can be written as summation of rank 1 tensors, and each rank 1 tensor is an outer product of a few vectors, right? So we learned all these. We also learned the multilinear operation. So with all that, now I think we're ready to learn how to do a tensor decomposition. And here we're specifically talking about an orthogonal tensor decomposition. Of course, this can be extended to linearly independent components, but it would require an extra treatment. So we'll hope to cover them, but if we couldn't cover them, I'll go through them really quickly because I really wanted to use the last 6 lectures we have left to talk about reinforcement learning. Okay, so if we couldn't cover the rest, so I'll leave them there, because I think the introduction of the RL is more important. And now I feel like the most important part of this lecture for the latent, latent variable model learning is to understand the moment matching. And tensor decomposition is a nice thing to have, to know, but I don't think it's as important as the concept itself of how to use moment matching to do to learn model parameters. So that's why I choose to cover what we can, but I think this lecture will be the last lecture for this line of topic. And from next week on, we'll switch to reinforcement learning. Well, actually, I will cover this book. So, can you see? My virtual background is making this hard. So it's Richard Sutton and Andrew Bartol's book. I'll cover part of the book for a quick introduction of reinforcement learning, but I wanted to focus more on deep reinforcement learning. Okay, well, we'll talk about theory of RL, of course, but I also wanted to spend deep RL. But we only have 6 lectures left. The last 3 lectures will be, course project presentation. Okay, so let's get started. Jennrich algorithm will be the first algorithm we use to understand how to do tensor decomposition. So again, I wanted to remind everyone what is the task. So the task is given tensor. So the tensor has an underlying structure that we don't know, but we wanted to recover, right? So this is, again, going back to learning the model parameters, wanted to do tensor decompositions to learn the model parameters. So given a tensor whose form is T equals to the summation of these rank 1 tensors, and each component is mu sub h. So h is the index of the component. We would have k such components. So notice the notation, so terminology I'm using here. I'm using component to denote this mu sub h here, okay? So h is the index for this component. So given these components with linear independent components, find the components, of course, up to scaling. Okay, so this is, the Jennrich algorithm. And it turns out, if you can see the figure here, you have a tensor that can be written in this form. And I'm again using this very simplified example of 2 components and, with the same scaling factor 1, 1 for each of the component. So, as we learned last time, the properties of tensor slices is that, we can have a linear combination of slices. So essentially, a linear combination of the slice can be written as this form, where you have this tensor of multilinear operation. From the first mode, you're doing an identity. So there is nothing happened for the first mode because your transformation is identity. And the second mode also identity, but the third mode is a vector, C. So this vector has, entries, and the entries are corresponding to the coefficients you use to do the slice linear combination. Okay, so C1 is the coefficient for the first slice, and C2 is the coefficient for second slice, and so on. Right, so you're looking at the frontal slices, and that's why you have the first and second mode to have identity mapping, but the third mode is a vector. Okay, so this is how you're doing frontal slices. Of course, if you choose to do other dimension slices, then it would be ICI or CII, right? Okay, so anyway, so we get this. So the linear combination of the slices, the following, and that, we learned last time that with high probability, the coefficients will be not equal, right? After your linear combination. So actually, this is the kind of intuition for Jennrich's algorithm. So the Jennrich's algorithm basically find this observation. What is the observation? The observation is that the linear combination of slices of the tensor share the same set of eigenvectors. Okay, so that's a very important observation, and we actually kind of hinted that last time. So the shared eigenvectors are tensor components. Okay. So here is the Jennrich's algorithm. So the task again is given this tensor with linear independent components and wanting to find the components. And the Jennrich algorithm is the follow, is in this algorithm pseudocode. So given a tensor, so the tensor is d by d by d, right? So you have the tensor. How does your algorithm work? So it has 2 steps. One is you wanted to sample C and C prime independently and uniformly at random from a sphere in the d-dimensional space. Okay, so you sample those 2 vectors, C and C prime, and then you are going to do the following thing. So you're looking at the eigenvectors of this tensor. So let's look at this tensor closely. So what is this tensor? So this tensor has 2 components, or not 2 components. This tensor has 2 parts. It has the first part of TIIC and the second part of TIIC prime, but pseudo inverse. So let's first look at the dimensionality. What is the dimensionality of TIIC? Remember, this is a linear combination of the slice, so it will be a matrix, right? because each slice is a matrix, and then linear combination of them are still a matrix, still a matrix. So this is a D by D matrix, okay? What about this guy as well? D by D, right? And then the pseudo inverse of this D by D would still be a D by D. So overall, eigenvector of a D by D multiplied with a D by D matrix. So it's overall just a D by D matrix, right? Okay, so basically you've reduced the tensor decomposition problem into a matrix decomposition problem by doing linear combinations of the slices based on the observation from the previous slide that we say shared eigenvectors are tensor components and linear combination of slices of the tensor share the same set of eigenvectors. Okay, so people wanted to ask the question of how is the Jennrich algorithm consistent? So actually it's consistent up to a scaling factor. So here is the analysis. So remember, what we're doing is based on this tensor, right? So this is what we are doing eigen decomposition on. So sorry, we have this tensor, which is actually a matrix. I call it tensor, but really it's just a D by D matrix. So you can see, because you have, these two tensors, the blue part can be written as U DC U transpose, right? So why can you do that? Why can you write that as a, so first of all, let's remember what is the form of the, T. So the T is right? And also, then what happens to TIIC? Right, this is your TIIC. This is the linear combination of the slice. So because of that, you can write them in terms of U, DC, U transpose, where U are just the stack of the U of the mu H's, right? So if you stack the mu H's, each column of these mu H's as the each mu H as a column in this U matrix, then this will be the U. And then the DC is nothing but a diagonal matrix with these components, inner product of C and mu H. So exactly like here, right? So, this can be written as U DC U transpose. Okay, any questions? Okay, so that I can write it. So by the way, I'm not doing any decomposition yet. I'm only doing analysis. I'm just saying the blue part is equivalent as this equation, U DC U transpose, okay? So now, the green, the red part is T of IIC prime. Similarly, can be written as this form, right? It is, very similar to the analysis we just had for the blue part. Now it has a pseudo inverse. That's why I have a pseudo inverse for the U, so the T of IIC prime. Oh, what happened? So the T of IIC prime can be written as U DC prime, U transpose. That's why the pseudo inverse can be written as this guy, right? If you have a diagonal matrix, and assuming that your diagonal matrix has no zero elements, then the pseudo inverse is just the inverse itself. right? And then you have the U pseudo inverse here. So that's why you have this form here, okay? So now you can see, because of the pseudo inverse, my U transpose pseudo inverse will be canceled, right? And that's why you have this U, these two diagonal elements multiplied with each other, it becomes, it is still a diagonal matrix. So you have this decomposition. So this U multiplied with this diagonal, multiplied with U inverse. Okay, so this is exactly an eigen decomposition. As you might recall, the first lecture of this course, we said this is an eigen decomposition, right? So that's why if you return the eigenvectors of this matrix, it would be your mu h hat, and it would be an estimation of these mu h's, and is actually consistent. Okay, so this is rather simple, right? So Jennrich algorithm, based on this observation that the component of the linear combination of slices share components, so they were just doing some linear combination, random linear combination, right? So you can see Jennrich algorithm is a stochastic algorithm in some sense, because it is doing some sampling from the sphere for the C and C prime, okay? All right, so by linear independence of mu h, so actually mu I said mu I here, but so mu I from 1 to k, and random choices of C and C prime, then we know that U has rank k. Okay, so this is almost surely U has rank k, and DC and DC prime are invertible, almost surely. And diagonal entries of DC and DC prime inverse are distinct. So remember, this is to ensure you have eigen gap, right? So the mu I from 1 to k are eigenvectors of this matrix with distinct non-zero eigenvalues. And therefore, you can say Jennrich algorithm is consistent. Okay, so this is the first algorithm. Seems like we've reduced a tensor decomposition problem with a linear independent components to a eigen decomposition problem for a matrix, right? So the tensor is d by d by d, whereas the matrix is d by d. So, through some kind of sampling and do a projection onto the third mode of the tensor, so that the projection makes the tensor from a third order tensor to a second order tensor, which is a matrix. Okay. So, so now, with this Jennrich algorithm, I'll actually introduce some kind of error tolerant algorithms for tensor decomposition. Why? Because when you think about, how we're using tensor decomposition for, usually the tensors that we observe are noisy, right? Because we only observe data examples and using data examples to form the tensor, like the empirical data moments, right? So these tensors are actually noisy, and we wanted to be able to have algorithms that are error tolerant. So this is the motivation, right? So with moments, expectation of fx are functions of model parameters, and empirical moments, empirical estimation of expectation of fx are computed using IID examples, xi, I from 1 to n only, right? So the example are like, you have third order moments, the distribution of word triples, which can be written in this form, as we said last time. And then the empirical third order moments are just the co-occurrence frequency of word triples, right? So the empirical estimation, just the hat of expectation x tensor x can be written in this form using your examples. So inevitably, the expected error of order essentially n to the power minus a half in some norm. For example, if you're looking at operator norm, then the operator norm between the expectation of x tensor x minus the estimated expectation of x tends to x tends to x will be upper bounded by something of the order n to the power minus half, right? So also the Frobenius norm is also in that form, right? So the Frobenius norm also between the expectation and the empirical estimation is also upper bounded by this. So actually, because we learned about concentration bounds, you guys can verify this. I didn't verify this in my slides, but you should be able to verify this if you have to. Okay, so this is just related to the concentration bounds we learned before. Now, we're motivated why we need to use tensor tolerant, why we need to have error tolerant tensor decomposition algorithms. Now we can check the stability of Jennrich algorithm. So is Jennrich algorithm error tolerant? So we're going to see that. Recall the Jennrich algorithm is, a very simple algorithm. We just saw it before. So basically, is an eigenvector of this matrix. Okay, so and the challenge is that we only have t hat that is very close to t, upper bounded by some kind of n to the power minus half. Now the problem now is, before you said Jennrich algorithm works well because you assume that you have the exact tensor, but now you don't have the exact tensor. You have t hat, which is an estimation of the tensor, right? So now what you can do is you can just do eigenvectors of these new tensor, new matrix here, right? So the tensor has been replaced with the tensor hat. Okay, so you would still do this sampling from the unit sphere, C and C prime independently and uniformly, and then you can just do like this transformation to get t hat of IIC and t hat of IIC prime pseudo inverse, and you then do eigen decomposition for that matrix. So now we wanted to check whether this will work now that your t hat is not the t, but it kind of is a noisy version of t. So to ensure eigenvalue gap for t hat of IIC and t hat of IIC pseudo inverse, so you basically need these two to, the estimation and the ground truth to be bounded by some kind of delta. Okay, so ultimately, essentially, by some kind of analysis, you would see you ultimately need the t hat Frobenius norm to be upper bounded by 1 over some polynomial of the dimension. So of course, I didn't do the analysis here, but this is the final result. My takeaway message here is that Jennrich algorithm is not very error tolerant. So we wanted to find some other algorithms to do tensor decomposition, especially for this error tolerant one. Okay. So how do we find those algorithms, right? Can we find a different approach? So we have some initial idea here. So in many applications, we wanted to estimate the moments of the form. M3 equals to summation of the omega h, AH tensor power 3, right? So the AHs are assumed to be linearly independent. So the idea actually comes back to when we were thinking about orthogonal tensor decomposition. So now we said, what if the AHs are not only linear independent, but they have orthonormal columns, right? If they have orthonormal columns, can we do something better? Can we have error tolerant algorithms? So that is how people find error tolerant algorithms for tensor decomposition. But of course, the caveat here is that you're not doing a linearly independent decomposition. You're doing a orthonormal decomposition or tensor orthogonal decomposition. Okay, so let's see. So what if AH has orthonormal columns. So based on this, you can see if I do a multilinear operation on my M3 tensor, right? So my M3 tensor is this form here, right? If I do a multilinear operation with my orthogonal components, AI, then what happens? You can see something will cancel out, right? So see, right? This is how, this is the definition of my multilinear operation, right? Like the first component will maintain AH because this is a linear operation with identity. So you will maintain AH. But for the second and third mode, you would have this inner product between any of the component AH with this specific AI here. Okay. So now what can you see? You can see that for any H that is not equal to I, because they are orthogonal, so it will be 0, right? So all the other H's will vanish except for this H equals to I. And that's why we'll see final result is just WI AI. Right, so you can see this very nice property here when the components are orthogonal to each other or orthonormal to each other. Okay. So before you couldn't see this, right? So this is very similar to this matrix eigenvectors. Remember when you learned about matrix eigenvectors, how are you defining matrix eigenvector? You're just saying that when I do a linear operation on a vector V, I maintain the direction of my vector. I was still in my direction of my vector V, but with some scaling factor. So this V will be my eigenvector, and this lambda will be the eigenvalue associated with that eigenvector. Okay, so this is how you define matrix eigenvector. Now think about this. Because you have this M3 of AI, right? So you are doing like a bilinear operation on this tensor through the second and third mode. And essentially this bilinear operation maintain the direction of the AI, right? After I do a bilinear operation for this AI, I still maintain the direction of AI. So this is very similar to this matrix eigenvectors. Right, so that's why we define the orthonormal AH as the eigenvectors of tensor. So before we said those are components, right? If AHs are only linear independent within these are components, we didn't say these are eigenvectors. But now if they're orthonormal, we'll see these are eigenvectors of a tensor. Okay, so now 2 questions. Essentially, we make this assumption that AH is orthogonal, but in general, AHs are not, right? So that's a problem. In latent durational allocation or in single topic model, we know that AHs are just linearly independent. They're not orthogonal. So what should we do, right? That's the first problem. And the second problem is how, even if they are orthogonal, how do you find eigenvectors of a tensor, which is error tolerant, right? Remember the motivation of why we do this is because Jennrich algorithm is not error tolerant. So we wanted to find an error tolerant algorithm, but how do we do that, right? How do we find eigenvectors of a tensor? So with these 2 problems, we'll first address this first problem, which is AH is not orthogonal in general. So what can we do? As I actually talked about it very briefly last time, we can do so-called whitening, finding a whitening matrix W. So whitening is the process of finding a whitening matrix W such that multilinear operation using W on M3 orthogonalize its components, right? So remember last time when we were talking about finding a W that orthogonalize these AHs, we find those VHs that are orthogonal. Right, so that's essentially the process of whitening. But I didn't tell you exactly how to find such W matrices. So now I'm going to tell you how. Okay, so first let's understand how whitening works. Based on this equation here, you can see M3 of multilinear operation WWW can be written as this form, right? This is simply by definition. Now we're saying that, you know, what are the components of these tensor? Is actually this W transpose AH. And we denote it as VH. So we wanted to make sure that W's are such that the VH's are orthogonal to each other. Okay. So how do we do whitening? First of all, I wanted to emphasize that whitening can be done by using M2, right? M2 is what? Is the second order moments, or you can think about using the empirical estimation of second order moments. Okay, so M2 can be written as the summation of omega H, AH tensor AH. You can see what's the similarity between these M2 and M3, right? So they both have the same coefficient for each component, right? And then the components are also the same. It's just that they have different order, right? So the AH is doing the tensor product for 3 power, whereas the M3 is doing AH tensor product for 3 power, whereas M2 is to do tensor product of AH for 2 power, right? So that's the difference, but you know, you can see a lot of similarities between the M3 and M2. So now you want to find the whitening matrix W such that W transpose AH are orthogonal, right? So basically you can see pictorially, this is what's going on. So, you know, we know that AHs have full column rank because they are linearly independent. Okay, because of linear independence, they would have full column rank. And it is an invertible transformation due to its full column rank, right? Because I can find its pseudo inverse. I want to make sure this is easy to understand. Okay, pictorially, you can see you have A1, A2, A3. They're not necessarily orthogonal to each other, but through this W transformation, you will have these orthogonal bases, V1, V2, and V3. Actually, I wanted to emphasize that usually the whitening matrix would transfer the thing into a smaller object. So for example, let's say your AH is in RD, right? So this is what we've been using, right? So this is the dimension of the data. So AH is in RD, so it's a length D vector. But now the VH, usually I would say is in R K, or you know, something like K prime. I don't want to, you know, confuse you because we've been using this thing as the K, but I used K prime for a purpose because usually this K prime can be very similar to capital K here, the number of components or the rank here. So the VH usually is in the dimension R of K prime, where K prime can be very close to K, the rank of the tensor. So the W would be something like D by K prime. Okay, so you can see what does this mean. This usually means that the W would be a tall and thin matrix, right? This is D and this is K prime. So it would project some kind of long vector into something that's rather short. Okay, so think about the interpretation here. So if you think about the topic model, then D is just the number of vocabulary English words. So it's hundreds of thousands words, right? Whereas the K is the number of topics in your document, in your corpus. Okay, so you know, maybe hundreds or maybe even a few dozens, right? So those are much smaller compared to the unique words in your English dictionary. So that's why we call it dimensionality reduction, because by doing this, finding such a matrix W, we're projecting this very high dimensional data to a very low dimensional space, right? So hundreds, right? From hundreds, thousands to hundreds. So it's really a dimensionality reduction doing this kind of multilinear operation on the tensor M3. Is this clear? Okay, so I will also show the picture here. As you can see, I'm drawing like a large tensor, being transferred to a much smaller tensor here. And the large tensor has linearly independent components, whereas the smaller tensor has orthogonal components, right? So we're using this multilinear transformation. As I said here, the dimensionality reduction, usually K will be much smaller than D, okay? So, but how do we find whitening matrix? So like I said, we're going to use M2. How do we do that? So we'll first find use pairwise moment M2 to find W such that W transpose M2W is identity. So you can actually show that if you make that happen, then W, so the problem is, if you make this happen, then you would make these vectors to be orthogonal to each other. Okay, so this is the basic idea. And now if you see, so how do we find W such that W transpose M2W is identity? What does this remind you? Eigen decomposition, right? So you just do an eigen decomposition on the M2. Okay, so actually because your M2 is symmetric, so it actually becomes U diag of U transpose. Okay, so you get this decomposition, and then your W would be nothing but this form. So U is the left, so the eigenvectors of your M2, and the lambda are just your, I don't know if maybe this is a little bit on the way. So you can see I'm only doing an eigen decomposition, right? So on M2, so I would find U and lambda, right? And then I'm gonna use U and lambda tilde to find my W through this form here, okay? So so basically I'm like separating the M2 into two parts, right? The left part is just like, let me write it this way. Right? I can also write it as like, right? And then right? I can write it that way. So basically we're saying that the W matrix would be this part, but this thing will be inverse. Okay, why? Do you want to see why? So if you can check in this way, the W transpose M2W will be identity. I can show you why, right? So you can now write it W transpose M2W as, so W is in this form, so it's gonna be diag of lambda and U transpose, right? This is W transpose. M2 is U diag transpose, and then, again, W, so it's gonna be U diag. Okay, so what is it? It's gonna be identity, right? So this is why we choose W in this way. Any questions? Okay, now I'll continue. So essentially, we say the V, which is W transpose A diag of omega a half, power a half, is an orthogonal matrix. And you can see now, you can verify using W of this form, the tensor will be actually the tensor would have orthogonal component. However, very importantly, the coefficients for each component has changed, but it's not arbitrarily changed. It is the original coefficient with power minus half. Okay, so that's essentially the reason why people tend to make mistakes when they are doing moment matching or using method moments to learn model parameters. They sometimes just understand, you wanted to do tensor decomposition and so on, but they didn't understand the subtleties of doing whitening, right? So especially during whitening, people forget that, this lambda h is not omega h, but it's omega h to the power of -1/2, right? So this very, the details might, it actually matters a lot in terms of final accuracy of the model estimation. So when I was working with my students on these kind of things, I saw a lot of mistakes related to these whitening matrix calculation and how to use it. So anyway, so I wanted to say this method is very powerful. It is very fast. It is very accurate, but there is a lot of details that needs very careful treatment. And sometimes you can make mistakes without noticing it. So, okay, so this is how we're finding whitening matrix. I wanted to see if there is any question here. It is not something that's easy to understand, right? So is there any question why this step, right, with the W being this form? Can we see why this is the scenario? Basically, you wanted to show this is an orthogonal matrix, right? Because this form here is essentially equivalent. So this is a vector of this matrix, right? Each column of this matrix is this thing here. So I wanted to verify it is an orthogonal matrix. I don't know if there is any question regarding that. But if you do, feel free to ask that on Piazza or discuss that on Piazza. Okay, I'll move on. So now we finally understood when AHs are not orthogonal, how we deal with it. So the answer is to do whitening, right? So the whitening not only can deal with that, but can also reduce dimensionality so that your algorithm is much faster. But the caveat here is that you still have to do a gigantic matrix decomposition on M2. Remember, the M2 matrix is D by D, right? So if you think about doing topic model, it's going to be tens of thousands by tens of thousands, right? So it's still a huge matrix, but there are a lot of ways that you can do approximations of decomposition on these huge matrices, and indeed there is a line of work on that. So in practice, we don't do D by D matrix decomposition. What we do is some kind of approximation of that. So essentially, you don't require this D cubed kind of complexity. Essentially, it reduces to something like scales with the rank of the matrix or of the tensor, and they're the same. Both are K. Okay. Okay, so that's the first problem. The second problem is how to find eigenvectors of a tensor. Okay, so now we're assuming that they are orthogonal, and again, the motivation is we wanted to find error-tolerant algorithms. So how do we do that? So let's first review the matrix eigen decomposition. I wanted to review actually the power method. A lot of you are familiar with that. So we first can, look at the property of matrix eigenvectors. So I call it fixed point because under this linear transformation, your vector maintain the direction, right? This is what we already talked about, right? So for this VI's are eigenvectors of the matrix. Then you do a linear operation, M multiplied with VI, which is just M of IVI. You will maintain the direction. It becomes lambda IVI, right? So the intuition, so that's the intuition for matrix power method. Linear transform on eigenvectors preserve direction. So now, given the orthogonal tensor eigen decomposition, you can see the task is again to find these orthonormal components, just like in matrix scenario. And you have this tensor in this form here. Now the properties of the tensor eigenvectors are also have a fixed point, right? As I said before, it is now instead of a linear transformation, is a bilinear transformation. You can see the tensor of IVI is a bilinear operation on this tensor using the eigenvectors VI. It preserves the information. It preserves the direction. Okay, so the intuition for tensor power method is actually different from matrix power method. Matrix power method is just that linear transformation on eigenvectors preserve the direction. But now this is bilinear transformation on eigenvectors preserve the direction. Okay, so these are like two different intuitions, but they are related to each other, right? One is essentially the extension of the other. Okay, so now going back to this power method for orthogonal matrix eigen decomposition. Since many of us are already familiar with this power method, so let's just go over it quickly, right? The task again is given matrix with orthogonal components, you wanted to find the components, okay? So that's the task, very simple. Now, of course, you're given the matrix. Of course, now I'm not talking about the noisy version yet. We will in a second, but let's first talk about the noiseless one, right? So you are given a matrix, right? You wanted to find the components which are orthogonal. So you do the following. You're doing a for loop, h from 1 to k. For each of the for loop, you're going to find the leading eigenvector. Okay, so how do you do that? Using power method. For I from 1 to t, so this basically means that you're do t times of the power method, two t steps of the power method. You're just looking at m of I ui minus 1. So the previous estimation of the eigenvector doing a linear operation with m. So m of I ui minus 1 is the same as doing a matrix vector product, right? And then you just normalize it, right? This will be a new estimation of the eigenvector. So you do this power method for t steps, and then you will get this ut will be your estimation for this component, right? And then your eigenvector will be m of vh hat. Okay. So once you do that, you basically finish estimating for the eigenvector and the eigenvalue for this component. And now you are just doing some kind of deflation. So how do you do deflation? You just subtract your matrix out, right? So for this component, you will delete it. And then, the estimation of the next leading eigenvector would be, again, doing a power method on this matrix, right? So this is the idea of the matrix power method for top K recovery. You're actually doing it in a sequential way because you first recover the top one, then the second top one, and so on. Okay, I hope this is clear. This is just a review of matrix eigen decomposition using power method and doing deflation. So now, well, is the question is, is this consistent, right? With whether the matrix power method is consistent. Of course, we all know that it's consistent. So basically it means that with high probability, the estimation of VH hat is the same as VH, right? So does the convergence depend on initialization? We all know that it doesn't depend on initialization. Actually, depends on the spectral gap, right? So now going back to, of course, these are the questions, we will answer them later on, but going back to the orthogonal tensor eigen decomposition, what would be an analogy of a power method in the tensor scenario? So here is the analogy. You can see everything is exactly the same, except for what I marked red here. So instead of, in matrix case, it is UI, M of I, UI, normalization. But now it is just a bilinear operation. Before it was a linear operation. Now it is a bilinear operation and divided by its norm. Okay, so this is just a matrix, sorry, a tensor power method. Seems to be very, very similar to the matrix power method. Then the question is, are they actually the same? Right? So if matrix power method enjoys some kind of nice property, would the tensor power method also enjoy that nice property? So again, you wanted to understand the consistency of the tensor power method, right? So, is it with high probability that's the estimation the same as the ground truth? Or, does the convergence depend on initialization, right? We know that matrix doesn't, but would tensor also enjoy this nice property that it doesn't depend on initialization? So let's see. So let's look at the analysis of consistency of matrix power method. And this is again a review of what we've already learned. So before that, we wanted to make some notation, to introduce some kind of notation so that we're on the same page. We want to order the eigenvectors in a way that is descending order. So it's like lambda I greater than equal to lambda 2 and all the way to lambda k. So this is in a descending order. And you wanted to project the initial point. So this is where you initialize your power method. So it's U0. U0, you wanted to project onto the eigenvectors. So presumably your eigenvectors are now just a orthonormal basis of the space, right? So any point can be projected onto these orthonormal bases. So you can get a CH that is the projection along the UH direction, sorry, the VH direction. VH is just the basis, the eigenvector basis. Okay, so you can get those, projection. So the convergence property is actually very nice. First of all, it's uniquely identifiable if and only if the lambda h's are distinct. Okay, so they're not equal. This is just a review again to remind everyone the unique identifiability. Now, the second property is that if the gap lambda 2 over lambda 1 is smaller than 1 and C1 is not 0. Actually, this happens with almost probability, almost surely, right? This happens with probability 1. So if gap of this lambda 2 divided by lambda 1 is smaller than 1, and C1 not equals to 0, the matrix power method converges to V1. The leading one, right? V1 is the one corresponding to the largest lambda 1. So what does this mean? This means that initialization doesn't matter, because the probability that C1 will be 0 is almost 0. So any initialization with high probability, it would converge to V1. So this is very important. You would always converge to the leading eigenvector, not anyone else, but the leading one using the matrix power method. Also, the convergence is linear. So it converges linearly to V1, assuming this gap. You can see this, this is the analysis here. So the linear transformation permits this form, right? So permits this form. This is nothing but just we've seen before. But more importantly, in T iterations, you will see this ratio is greater than equal to 1 minus k of lambda2 divided by lambda1 to the power of 2t. So that's why it's a linear convergence. Okay. So this again is very simple. You can just use power method to write it out. And by doing very simple linear algebra or simple calculus, actually, you will get this. Okay, so it's the ratio of the second and the first eigenvalue and to the power of 2t. So that's why the convergence is actually linear. Okay, so this is a review of the consistency of matrix power method. What about the consistency of tensor power method? So you can see we can also do this same definition of the terminology. We can project the initial point U0 onto the eigenvectors, right? So this is again the initialization of my power method. I can again project onto my orthogonal basis, actually also normal basis. And then I can order the eigenvectors not on this lambda1 greater than lambda2, but on this thing. So I have this extra term here. The absolute value of these projection coefficients. So as long as I order it this way, so lambda I multiplied with absolute value of Ci. So Ci actually, denotes to like this Ui's projection onto this basis, right? So the multiplication of the two would be the thing that I'm ordering. So the reason why I'm doing that, you'll see in a second, right? So we'll see the convergence property. So first of all, the identifiability is no longer on this lambda h's. It is actually on this lambda h multiplied with this absolute value of ch. So this is concerning, right? This means that initialization actually matters, different from the matrix case. Okay, that's the first property. And then the second property, this is not surprising that now you require this quantity to be smaller than 1. So this lambda2 multiplied with C2 divided by lambda1 multiplied with absolute value of C1. You require that to be smaller than 1, and you require this quantity to be non-zero in order for converge to V1. So what does this mean? This means that you not necessarily converge to the component that has the largest lambda, right? So because V1 does not corresponding to lambda1 that is largest. Actually, V1 corresponding to this quantity is largest, right? This quantity is largest. This is what V1 is corresponding to. So initialization matters, right? So it's not only lambda1 that will be recovered, the component that has largest lambda1 is recovered. Is actually the component that has largest lambda1 multiplied with absolute value of C1 that's recovered. So initialization matters a lot. Okay, so that's very different from matrix. So the idea is the takeaway message is that V1 is not necessarily the largest eigenvector. And what's interesting to see is one benefit of doing tensor power method is that it converges quadratically. So it's not linearly, it's now quadratically because of this term here. So it's this ratio to the power of 2 power of t plus 1. So it is much faster than a matrix power method. Because matrix power method converge linearly, here it is converging quadratically. Okay, So the benefit of you're getting from doing tensor decomposition or tensor power method is that you converge much faster. However, you have to pay the price that the convergence depends on your initialization. Okay, so this is for this slide. I wanted to just very quickly compare the two. So matrix power method iteration requires the gap between the largest and second largest eigenvalue. And so it only depends on the property of the matrix. It doesn't depend on the initialization. Whereas in tensor power method, it requires the gap between the largest and the second largest lambda HCH, the initialization, right? So it's not only the property of the tensor, but also the initialization of the power method that matters. Okay, but for matrix power iteration, it always converges to the top eigenvector. Now, which is very nice because we can very easily understand, whether this is a leading eigenvector based on what it converges to. But for tensor power method, this is no longer true, and this could cause problem because we're not necessarily recovering the component that is largest. We might be very unlucky and have a very bad initialization that puts a lot of weight on a small component. And therefore, this lambda h multiplied with absolute value of CH is very large, larger than anyone else. But actually, the lambda h is very small. So basically, we will be recovering an unimportant component, right? Doing under this very unlucky initialization. So that's the problem for this tensor power iteration. But the nice thing about tensor power iteration is that it's quadratic convergence, whereas matrix power method is the linear convergence. Okay. All right. So actually, I'm gonna skip the spurious eigenvector for tensor eigen decomposition because I feel like this is not necessarily very important for our purpose. But if you are curious, you can take a look at the slides. And I think it does provide a very interesting perspective on why doing tensor power method or tensor decomposition could be very challenging. But the nice thing is it's very fast, right? If you know how to do it, it's very fast, but it is very difficult. Okay, so from an optimization viewpoint of tensor and matrix decomposition, again, it's very important if you are working on it. But I don't have time, unfortunately, to talk about it. So please read it when you have time. And I think the slides are pretty explanatory. So you can just read the slides. And if you do have questions, please feel free to ask me on Piazza. So the question here is the performance under noise. As I said earlier, the motivation of why we look at the orthogonal matrix or tensor decomposition is because hopefully they will be robust under noise, right? So here are some results about the tensor perturbation analysis for this power method. So the takeaway message is that it is actually indeed noisy, robust. So that's why instead of using Jennrich algorithm, we tend to use power method. Of course, I don't have time to go through the proof here, but the takeaway message is that you can allow some kind of noise tolerance, which can be calculated here. So you can look at my slides here. So, so basically, it means that you can have a polynomial sample complexity for learning. So in terms of the number of examples you need to have to making sure that your tensor perturbation, so to make sure that your estimation, the empirical estimation of a tensor is close enough to the ground truth tensor, you only need polynomial sample complexity, okay, for a power method to work. So of course, the tensor power method is the method that we learned before was just one step toward our understanding of tensor decomposition. There are many other algorithms that are advanced versions of this. For example, you can have simultaneous power method. So before we learned about doing things sequentially, right? First recover one component, then recover the second component, and so on. But we actually have a way of recovering them simultaneously. And this way, this simultaneous power method actually allows you to recover the component with the largest eigenvalue, so which is very important for the tensor decomposition algorithm, because you do care about the larger components rather than the smaller components, right? And we know that the initialization really matters. So this paper actually has a very nice way of doing initialization to make sure that you recover the largest component. Okay, so there are other papers like orthogonalized simultaneous alternating least square. This is yet another algorithm of dealing with tensor decomposition. And then initialization really matters. Actually, there are papers specifically allocated to specifically talking about initializations of tensor decomposition. For example, using SVD, or using some kind of trace-based initialization. Okay. So finally, I don't think I have a lot of time to talk about this, but I wanted to give you a very brief idea of how tensors can also be used in neural networks. So before I talked about tensors used in moment matching or learning latent variable models, right? So actually, those methods have been used to learn neural networks, right? So to learn two-layer neural networks, and people are working on extending it to learn multi-layer neural networks. But here, I wanted to take a different perspective. I wanted to introduce a way of doing tensor representation in neural network for compression. So instead of representing neural networks, let's say convolution layers of neural networks as a fourth order tensor, we wanted to represent it as decomposition forms of the tensor. So it's like a factorization of the original convolution kernel, and essentially you can achieve model compression without much loss of information. Okay, so it's kind of like a low-rank decomposition idea. So here I'm just motivating why neural nets are very important and successful, but they require a lot of data, and the model is getting really, really deep. Okay, so again, this is just a figure of showing why models have been so deep, and essentially they're getting more and more deep over the years, and therefore the model is larger and larger. Okay, so basically the challenges for these large networks for learning is okay, it's just like a one-time cost, right? You can have a gigantic GPU cluster to learn your neural nets. It takes longer, but that's fine. It's a one-time cost. But more importantly is during test, because you have this repeated unseen data coming. So you have the cost for every time you're doing a prediction. So it's a repeated cost. And it requires a large amount of computation, memory storage if your network is really large. And that's the motivation of why we wanted to do model compression, especially if nowadays we're doing personalized machine learning, federated learning, right? So you might do machine learning on your smartphone or your camera, but you don't have a large memory in your Internet of Things device, right? So you wanted to have models that are smaller. So the motivation of doing model compression. So the question here is how to compress neural networks without much performance loss. So basically what I did in this slide is I introduced different kinds of tensor decomposition. I think of them as a representation of the data. So I can represent the kernel in my neural network as tensor decomposition forms. So you can also think of it as a reparameterization of my network. Okay, so here I'm introducing CP decomposition or Tucker decomposition, but there are nothing but a tensor representation of the original convolution kernel or fully connected kernel. Okay, so then I said, actually, you can see you can do a compression of a convolutional layer with respect to tensor decomposition. And essentially we say for a convolutional kernel, you can think of it as a fourth order tensor with the height, width of the filter and the input number of channels S and output number of channels T, right? So you can think of it as a fourth order tensor. And essentially what we're doing is we're going to do a decomposition of the fourth order tensor. Okay, so if you see that, for example, if you do a CP decomposition, then you're decomposing the fourth order kernel into this form here. And you can see actually the number of parameters have been reduced to this form. The R is the rank of the decomposition. So if you allow R to be smaller, then apparently this thing is much smaller than this thing here. Okay, so the number of parameters in your network is drastically reduced. So this is just one example that I'm showing here. And you can also use Tucker decomposition, of course, as a different form of doing the decomposition, where you can think of it as a different way of doing the reparameterization. And you can also achieve some kind of parameter reduction. Okay. So you also have the tensor train, which is another way of doing the decomposition. And finally, I'm just saying that if you have some kind of reshaped tensor decomposition, basically what I mean is you can reshape the fourth order kernel into a higher order kernel, then you can have more aggressive model compression. And essentially here I'm showing if you do some kind of reshaping, then you're drastically reducing the number of parameters from this term to this term I'm showing here. Okay, so again, I don't expect you to know all the details, but the takeaway message is that not only you can do tensor representation, but you can reshape your fourth order tensor to be an even higher order tensor and then do tensor decomposition on that higher order tensor. You can get an even more aggressive compression without losing much information. Okay, so these are just a few different examples. I'm also showing some results, so I don't want to go through that in class, but if you're interested, you can look at the results. Okay, so finally, just to conclude, so method moments can efficiently estimate the parameters for many latent variable models. For example, mixture of Gaussian. For example, single topic model. For example, latent Dirichlet allocation, right? So all these kind of models are the traditional latent variable models that are proven to be very useful for a lot of scenarios. But now if you add some kind of nonlinearity to it, then this becomes a generated model like in GANs or VAEs, right? So the difference between these latent variable models, actually, if I wanted to be more precise, I would call it generalized linear latent variable model, right? So if you add some nonlinearity, then it actually becomes a generated model sense in the deep learning, generated model in the deep learning sense, okay? So this is exploiting the distributional property. And kind of multi-view structure and other structure to determine usable moment tensors. And some efficient algorithm for carrying out the tensor decomposition to obtain the parameter estimation is also discussed. And then we talked about tensor decomposition. Actually, we could also do tensor decomposition for neural networks on the weights of the neural networks to compress the network, as I discussed earlier. But there are many issues to resolve. For example, there are this model misclassification. We don't know how to deal with them. what if you have more noise? How would you deal with those model misspecification, right? This again is still an open question. And then finally, learning deep neural network parameters using tensor decomposition seems to be possible, but there isn't a concrete algorithm to do that yet. We only know how to do a 2-layer neural networks, but we don't know how to do a multi-layer. Okay, so finally, I think that's the end of the lecture for latent variable model. And from next week on, we'll focus on reinforcement learning. So like I said, we'll introduce very quickly the basic concepts of reinforcement learning, and then we'll go to the deep RL. Okay, thanks everyone. Oh, by the way, I'm still grading your project progress report, so I'll make sure I send my comments back soon. Okay, thanks everyone. I have to go get my alarm. My phone is not here.